All right, everyone, thank you for making it out to our invited seminar today. Today it is a pleasure. So today is a really, really great honor to have Rajbabu Velmurugan presenting. Rajbabu and the contingent that has come from Indian Institute of Technology, Bombay, have been collaborating with us on digital agriculture projects for the last year. And it has been a real pleasure to work together alongside. And recently they hosted me in Mumbai. And now we're very fortunate to have them back out. So Rajbabu is a professor in the Department of Electrical Engineering at IITB. He received his PhD from Georgia Institute of Technology in 2007. He was at LT India from 1995 to 1996, and then MathWorks until 2001, when he joined IIT Bombay in the area of signal processing. He also works with inverse problems and with application in image and audio processing, such as blind deconvolution and signal source separation. Today, Rajbabu is going to talk about his ongoing work in crop disease detection and classification with machine learning. And with that, I will hand it over to you, Rajbabu.
Good morning, everyone. Thanks, Chris, for that introduction and welcoming us to IIT Bombay. So today's talk, as Chris said, is about crop disease detection and classification using machine learning. This is some recent work which we started in the last year and maybe a little more than a year. So the work which I'm presenting is mostly possible because of the work with the two students here, Siddharth Kandelwal and Sean, for both BTech and MTech students respectively at IIT Bombay and graduating this year. And Professor Mariam, who's also a colleague of mine in our department. And Professor Biplab, who also works in this area of machine learning. As you can see, we are all from electrical engineering or resource engineering, and we are not really the agricultural specialists. So this is our attempt at to look at and help solve this problem. So let's see what this talk is going to be about. So this will be the outline of my talk. I'll give a brief background as to why we are looking at this problem. The focus more is on the image processing and machine learning aspects of detecting or classifying or predicting. We have done parts of these, not all of it. And how we started off with a generic data set and models existing in the literature or being used already for solving such problems. And then how we tried extending it to something which is more relevant for us initially locally, and then trying to generalize this to more data sets and more crops. And that's kind of our objective. So the main motivation, after several discussions, of course, all of this is part of what we have as a technology innovation hub at IIT Bombay, where it's not just research, but this research leading to some, let's say, product or something which is going to have some local and social impact. So with that in mind, we are located in Maharashtra. Mumbai is in Maharashtra, a state which is known for onion. An onion is not kind of a rich man's crop in some sense. It's very, very much used. And one of the challenge there is, at least in India, the pricing of onion is kind of unpredictable. That's a very difficult problem for us to solve. So what we intend to look at is what aspects affect onion yield. This is a problem in general in agriculture. And so this is just I'm using this as a motivation to see why we wanted to look at onion as one of the crops. So as I say, as shown here, whenever we are looking at yield for a specific crop or a product, there are several factors affecting it, starting from irrigation, weather, And using this, the plant grows, but then there can be things which affect the growth of the plant, either because of a disease or a pest affecting the plant. And onion also has these problems. And one of the, of course, weather is something which is very unpredictable and has a larger impact, but these two also play a part. So it's not in isolation we can solve this problem, but our attempt is to look at how to solve this problem if we are just looking at images and trying to predict these diseases, so that we can come up with preventive measures, so that overall we can address this problem of either bad onion quality or less production to increase the eventual yield. So summarize, so there are many aspects of this problem, which is what the bigger objective of this project was, starting from when the focus, as I said, will be on disease and pest attacks and how do we infer those. There are other aspects which I'm not going to talk about much in this talk, but just to give you a sense of how the system is, I'll probably present an overview. Specifically, the reason I talk about predictive models is eventually we want to use these other parameters which also play a part in this crops or plant growth. And the way we use images is mainly for the inference part, in the sense like, has something affected the plant? How do we determine what affected the plant? And of course, there could be other parameters which we measure, but currently we are focusing mainly on the image analysis of it. Once we have this kind of both parts taken care, what we intend to do is kind of this global, the major goal of trying to develop this decision support system, which is most likely should be cost-effective solution that could be used by farmers. It takes inputs from all those parameters which I talked about. Those are local parameters sensed using sensors, and as well as images of the crop or the plant, which we are using it as a feedback. So if something is affected, how do we know it is affected? So as of now, we could look at other things like other parameters like soil moisture and efficiency of fertilizer, measure this using some other aspect. That's not we are going to look at in this talk. We are mainly looking at images. And at later point, once we understand both of these, we'll be able to correlate how one of these deficiencies affect and how they show up in the image. So this is the big kind of system which we have in mind. This is when there are many parts to this, and I think my focus I just want to show here is if you just think of this system where you have several sensors deployed in an agriculture farm, they may communicate locally or through the cloud to a data server where some of our inference algorithms may be running. And based on this inference algorithms we do some predictive analysis and give feedback to the farmer. So this feedback could also involve humans in the loop. Again, that's something which is for future work. So here mainly the focus is, as I said, if we can capture images here, what could we infer from these images? So we are not the first to do such things. There has been work, and some of them have been even recent, where people have used this multi-parameter as inputs, use images as a mechanism to infer what happened. And then, of course, as was popular happening nowadays, there are a lot of deep learning work being used in the field of agriculture as well. And they try to form a closed loop system, including everything which I mentioned, like irrigation, and then if needed, how to apply pesticides. Together, how this important system works. There's some work which has been done recently, but this was for the potato crop. There are some differences. Of course, as an agriculturist, you can always look at these crops, or biologists, you can look at these crops and come or understand many more differences. For us, we wanted to look at from if the process is using images and capturing images to detect diseases, are there differences across crops, plants, or is it all same? Once one is done, can we just use it? So that was one of our reasons why we wanted to look at it as a different crop, which is onion. Similarly, the image-based analysis has also been done. Again, even using ML, and these are somewhat recent works in the past 2 years. But these were different diseases which affected onion in a very different setting. Just to say that, I mean, this is work which is being kind of interest to many people and not just us. So some of the challenges because all of those who are in machine learning always know that to get good models and good inferences, you strongly depend on the data which you collect and how you label them. So again, so we intended to do that because we have resources to do such data collection for this specific crop. Because the starting point would usually be this classical techniques, and which we also attempted. But then we also wanted to go forward and look at machine learning approaches, because if you have large amount of labeled data, then I think it's good, and machine learning approaches will also help. But there are in the problem which we are looking at least in India, data collection and labeling has not been done a lot. There has been some work, but not a very methodical work. So which means we may end up with data which may be large, but these are not labeled data. So that's again a challenge. So we wanted to use this both as a challenge to solve the problem and as well as a machine learning challenge as to see how to address these issues. The last point, as I said, human in the loop may actually be part of our final system. That's something which we haven't looked at much. So as you would expect, for those of you who've done image-based classification detection, this is also, we also follow the same pipeline. So we plan to use, or we have used images of either plants or leaves of the plants. There is a slight difference between using just the leaf versus the plant itself. So we'll see why that is important for us. And then, of course, just identifying, detecting, and classification. Slightly, the way we are looking at identifying is just saying, okay, is this healthy or not healthy? Detecting, again, is somewhat finer detection of the healthy and non-healthy ones. Whereas if you say about classification, this can be more than healthy and non-healthy. Among the non-healthy plant, there could be several diseases or pest attacks which cause this deficiency, or and then how do we classify them, right? So the approach we took, which what you would usually do, is have models which do very well in terms of classification. So can you just take them, adapt them, or transfer learn from those models and apply these on the data sets which we have? So that's kind of the idea we had. But additionally, we wanted to also look at some of the pre-processing aspects. This initially we thought this is going to be a big impact, but you'll see it did have an impact, but maybe not that much as much expected. Again, since this is some yearly work, we also just didn't want to say apply the models, get the results, and go away. We also wanted to understand what caused this decision. For those again who are in machine learning would be aware of this GradCam based approaches, which essentially say where our inference is driven by what we expected the inference to drive. Right? So that's something which I'll probably show later as we go forward. So the starting point, as I said, was a generic data set. The only common thing here, this has this name plant, which means this is closer to agriculture. And this was one of, at that time when we started about 2 years back, one of the largest data sets of which had crop or plant related data, which is a very clean data in the sense, as you can see, all the leaves which are shown here are in a background which is quite distinct from the leaves itself. And there are several plants here. So like as mentioned here, there is 38 plant species looked at. Each of them has different diseases, and this was a data set collected, I think, from some region, Kenya, probably Kenya in South Africa. And then there are many works which have used this data set to do similar things as what we have done here. Right? So the point here is like there we have about 50,000 images, which is still not as high as ImageNet or any other thing which is used for standard object detection and classification. And the classes, of course, are also not that high for us compared to a standard ImageNet data. But since the total number of images is already less. This is still high for this number of images. Let's just see. So now, having seen these images for what this plant village data set has, we wanted to see, okay, so now what happens when we go into onion, right? Again, as I said, just to re-emphasize, onion is important for India, and so India accounts for most of the onion population in the world, and we wanted to look at how the standard or existing convolutional neural network model perform, and then how do we exploit them, or how do we improve on them to do better. So the data set which we had, I'll just show the images soon. Roughly, we have about 800 images. So to compare the 50,000 images we had for this plant village data set to the 800 or so images we have for this onion. And we just say this is a data set, but it's actually just a data. The data was shared partially by some of the scientists who work in the field, agriculture scientists. And these images were just WhatsApp or some images which farmers had sent. So this is no way, I can't say this is a rich, wild data set, nor is it a rich, organized data set, just data which came. So based on that, this is what we had. These are things which affect an onion crop. So again, here you can see the imbalance in data, and that's what this histogram says. So for this bulb rot, one of the common onion diseases, you have large number of images, whereas if you look at this purple blotch or iris yellow spot, the number of images we have are very, very small, right? So though initially we thought we should start and classify these diseases, given this imbalanced data, we wanted to just look at binary first. Right? Just to give you a feel for how this data looks like, compared, you can just recall how the plant village data set was. So these here is, again, it's a healthy onion crop in the field. And there are some other diseases. So for example, this is the damping of disease where you can see the fruit of the plant going down. Similarly, bulb rot actually affects the bulb of the onion. And then the Staphylium anthracnose is a bacteria infecting the plant. And there is this iris yellow spot. So the reason I am just showing this is one of the challenges we had in this data set is, if you think of this healthy, this is an image captured, let's say it's a long shot. We don't have too much details. Whereas if you look at the images shown here or here, these are images taken nearby, nearer and closer to the camera. So which means the details are preserved more, right? And if this is going to be done from a field, you can't expect what this data could be. So a challenge was to say a model should not be driven just by the, let's say, the scale of the data, and it has to look for some other information which says, oh, this is healthy or not healthy. So this is very much different from just the leaves which we saw in the plant village data set. And hence I said leaves are important, but maybe in the onion, it's actually the crop. What you see here is the shoot of it looks like the shoot, but it's the leaf which comes off from the root. Right? So, and then the angle or the way you capture this image can also make a difference. So we wanted to look at all of this. So, but all this seemed more challenging. So we said, okay, let's just start off with kind of a binary classification of whether or not this onion crop is infected or not. Right? So what we did is as kind of effective as usual in machine learning based classifications. We start off with one of these existing models, DenseNet architecture or VGG or ResNet or AlexNet. Initially, we started with the ResNet architecture. Later, we ended up using a DenseNet for reasons which you'll see and show soon. But the idea was you have these basic models trained on ImageNet for object classification. We use this approach with the motivation that since plant village at least has some commonality to the crops and plants which we are looking at, we train it or retrain it using this plant village. So that's our starting model. And then from there, we use our onion dataset to kind of transfer learn and detect, is this a healthy or non-healthy plant, right? So that's what is shown here. So in some sense, you can think of this as just a feature extractor. Then you use this feature extractor based on ResNet or DenseNet fine tune it first with plant village so that the weights get updated, and then use that model and then remove the layer corresponding to the plant village. In plant village, you have 39 classes. So we remove that and instead use just 2 nodes for the onion data set so that we could classify if it is a diseased or healthy onion, right? This kind of is a reasonable approach. And given this data set which we had as shown here, so we have about healthy onion images of 102 and diseased 644. As you can see, the imbalance is already there in the data set, even with healthy and disease. And of course, when I showed disease itself, there were several classes. But for now, we didn't want to worry too much about it, as we just wanted to do the binary classification. As is usual, we use to handle this data imbalance, we use this data imbalancing where sampling of data where we make sure that this imbalance is taken care in our training and later user testing for that. So we have given some of the basic parameters here. This is most for if you're interested in reproducing, we will be able to give more information. But just to give the context, so the points of interest here is maybe just the batch size and as we saw the number of images in the plant village compared to the number of images in the onion disease, right? Other than that, these are other standard machine learning parameters which you want to use. So once we do this, so this table is just to say which of the models we wanted to use going forward for our onion. We experimented with these different architectures. As I said, we started off with ResNet initially, and then went to this ResNet 152, which is a larger model. We got good accuracies of let's say 98.5%. The model size was in 200 MBs. I compared this with DenseNet model, which is of smaller size, and the accuracy was reasonably close to what we have got with the ResNet. This was mainly because we wanted to further, for experiment we wanted to conduct later, we wanted a good model to start up and eliminate model which we think will not be very useful. Again, the objective is not just for onion, for now it is for onion, but we want to see how these things can generalize well. Right? So that's kind of the reason or motivation for comparing these different architectures. With that DenseNet model, we had a test set of this onion, again, binary classification. So this is just saying the kind of accuracies and F-scores we obtained with and without augmentation. Because we are still experimenting with this kind of augmentation, because our goal here is not just to get good, let's say, either one of precision or recall, but instead we do want to have reasonably similar precision recall accuracies, which are high. Essentially, our F-scores need to be high, but also not at the cost of precision or recall. So this is why we still, this is some part of work in progress where we are looking at data augmentation techniques, which will help us achieve better results. Of course, with the given data, we are somehow limited now. So we are in planning for more data collection and see how that data collection will help us in this experiment. So this is with the onions, kind of summarizing. So based on the plant village inferences we had, when we apply this DenseNet model to the onion data which we have, kind of as expected due to the data imbalance, this was the best accuracy we got. And we are hoping that we could do better in terms of accuracy as we get better and meaningful data for the onion data set. So this is what I mentioned about this GradCam. So essentially, GradCam is once you have trained and obtained your model, you can think of GradCam as a kind of a validation of your model, so that you understand if you are given, let's say, a source. Sorry, I don't have the original image. Assume that I give the original image as the input to this model, which has been trained. So now it is in a kind of the testing phase. So when you apply this, GradCam is the it runs the back propagation algorithm on the given source image and says, okay, these regions based on the weight propagation and acting on the original image, these regions, say for example, where it is red here, this helped in making that classification or inference. So for example, if this is, this corresponds to if it corresponds to a healthy image, it would say, okay, this part of the, so then in this case is disease, actually disease 1. So this says this is the region which made the model design, this actually cause, it has a disease, right? And similarly, if it says it's a healthy model and these red regions here actually made the model think that this is healthy. And similarly, another example of why it thought it's healthy. So I think we don't want to rely on this just now 100%. But what we could at least say is these decisions are not based on these blue regions here. These are regions which correspond to the most of the onion plant in the image. So that's kind of one of the takeaways from this. Because initially we were kind of tripped off with another experiment where we thought the model was working fine, but then we realized it was actually something in the background which made the model decide that this is healthy or unhealthy. So with that in mind, when we tried this model, this did show us that is indeed models are doing what we expect them to do. But this doesn't scale or go forward when we try to classify, and that's where the challenge is. So we cannot go beyond these two classes. So we tried doing this with it's the same data set, but rather than doing a binary, we said, let's restrict to a subset of these classes where we have reasonably larger images, let's say 25 or 30. And we tried to do this multi-class classification. I mean, this was just as an experiment. We wanted to make sure that we are somehow in the right direction. As you could see, this in this multi-class of these 4, 1 healthy and the remaining 3 being unhealthy or affected crops, we could only achieve like 78% accuracy, which is not good enough for this problem. And this is a challenge. So, but I don't want to say that it's not possible. The only comment here is because of the data we have and the data set we have with restricted images and the imbalance, there could be many factors which affect this. And this is some work in progress, which we hope will be able to do better as and when we collect more data. So this is a little more on the machine learning part. So if there are doubts at a high level, do let me know. I can say a little more. But assuming that you know a bit more about machine learning, what we also wanted to try is, so given lesser amount of data and possibly incorrect labels, can we do other traditional, when I say traditional, more popular, let me not say traditional, more popular approaches to handle these problems? Like if you have a data set, a smaller data set, few shot learning is one of the popular techniques which people have been using. Of course, now there are many more things like foundational models. So we wanted to experiment these things and see, do these just directly apply to the data sets which we have? So in that attempt, we looked at few shot learning. The idea in few shot learning is, so you have, to begin with, you have a large model, like say, for example, ImageNet kind of thing, where you train a good model based on a very large data set for the problem you're interested in. So then you have a smaller data set, which is more meaningful, more relevant to the problem you're trying to address, which has labels and classes understood, but you have only fewer images. And then finally, when you want to apply it to your problem, then images are even lesser. And so how do you make your inferences? So the starting point for this is what is called as this meta learning, meaning you have a large model to begin with, trained on a very huge data set. You use a smaller data set to fine tune your model. That's this meta learning. That's when the model learns. But this data is more relevant to the problem you want to solve. And then finally, when you test, you're actually testing on a data set which is even more smaller. You don't have too many levels. So that's the idea. So here, this n-way k short is, if you have n classes and you have k of them labeled. which means that's also a challenge here. So this is this at this point, we don't have any problem because we could get this for most problems. And then the query is the images which need to be, this is a kind of a test visually done, right? Given these few samples, you want to classify them and say which are these classes among them. So this meta learning is a well understood idea in machine learning. And we wanted to try this meta learning in the data sets which we had. Again, we may be doing something very extreme, but we still wanted to try how these things work. Let me just show the setup. So this is the part where so now the focus is not only on just a binary classification, but among the classes we have, these have a little larger number, like say 100 or so in each of these classes. So this is our, in some sense, the one which we use in our few shot learning to retrain or learn the features which we think are more important for our problem. And then try this, once these features are learned, this novel set is a set which we want to test our model on. So now we don't have, as you can see, there are very few images like 5, 9. We don't actually train on them. We just like, we have learned something, there is a prototype. I apply this prototype on this smaller data set and see, can I classify these images? So when we do that, I mean, this is what we got. It's like, which is actually not doing much, though we started off with a very systematic approach to solve small data set issues. So this is not to say that few shot will not work. It's just that the way we have the data right now, there are many, as I said, there is a lot of data variability. We don't need to know whether these are images of similar nature, images captured in the same setting. So it's like really a problem in the wild. So I don't want to say that few shot is not going to be applicable for such problems. It's just that the way we had the data doesn't seem to help. Yes.
Rajbabu, is that anything twice as good as random? What would a random?
Yeah, it should be, yeah, it should be not even, yeah, somewhat closer to random. We got 4 classes and it's trying to classify them. So yeah, as good as random. Slightly better, but whether that's a good number to go is not very. I mean, the reason I'm not too positive about this is for example, some of these things we have very few numbers. That's like it's like just as good as random. I say this and say, okay, is it not? So this is again I mean, more driven from the ML part. Foundation models are now very popular, the chat GPT and other things. This is when they started coming, and we wanted to see whether such things are applicable here, because it suited our problem because we have data, some of them labeled, some of them are unlabeled, but we know what the labels could be. Right? So with that, so we wanted to look at this specific model, which is called as CLIP. Essentially, again, this came from NLP and other areas, where in this case, the training is, the CLIP is, if you think of as a foundation model, the way model gets trained is a huge data set, but it's kind of correspondence between the image and text is being exploited. So there is an image corresponding to, say, for example, in this case, dog, puppy, and probably its name is, I guess, paper. So this is a text corresponding to an image, and you have many such image and text correspondences. This model is trained, and when it is being tested, so you may not have a image with the corresponding matching label, but you know that there are possibilities, these are the labels, and then you apply your image to the image encoder and see, image decoder and see what is the label corresponding to that image. So we thought, since we have, of course, our images are limited, but we want to try with the plant village dataset whether such models could be used. Plant village dataset has about 50,000 images, which is much higher than what we had, but we still wanted to try in the plant village dataset itself how well could we do. So where, if you recall, we had like 98, 97% accuracies in the standard models which we had, and then we want to try what happens with these foundation models. We could achieve about 85% accuracy. Again, this is not to say this is the limit. There are, I mean, more work on this CLIP models The challenge here is, so as I said, this text here is referred to as the prompt text. So which prompt to use is also kind of decides how well your model will do. For many of these problems, this seems very easy to do, but for the image plant disease classification problem, maybe that could help us, and so that's why probably we have this 85% accuracy. It's like, I mean, just to say, I mean, this part is difficult. That how to come up with appropriate prompts for the problem you're looking at is a challenging thing. So that's one of the reasons. And then also we were, as I said, we were motivated to not just come up with good ML model. We wanted to solve the problem. So we said, let's keep this on hold and revisit it if we get more and better images. So to summarize for the onion part, so I think the basic models, which let's say DenseNet or ResNet, they seem to do well, and fine tuning them with plant village, and then on applying it on the onion dataset gave us reasonable accuracies. There is scope for improvement, but that could just be dependent on the dataset which we have. Multi-class classification, again, I think we have things in place, but for the dataset we have, we will not be able to do any better. This future work will involve more on this few shot classification and how to use it to do multi-class. So that we still feel this is useful because we don't expect all the images which you're going to capture to be labeled. So in that setting, this is actually going to be a more powerful tool once we start getting more data. At this point, that's all I wanted to say about onion. But as I said in the beginning, we also looked at other crops. So there is a slight, so far I said detection and classification. I just want to say that the way we are looking at this is also can be thought of as a prediction. The reason is, I mean, there is no point after you find the disease or this is diseased or non-diseased. So we wanted to use similar a detection approach to do prediction. And so I just wanted to show what we tried doing it. This is again preliminary work, but I mean, you may think this is the same, but there is a subtle difference. So here the crop, of course, changed. We could have tried with onion, but we didn't have such images for onion. So we looked at having controlled experiments where we could collect data in a kind of time-stamped kind of way. So images over as the plant grows or as the crop grows, we collect images. So we had two groups. One, again, this was work mainly by Professor Mariam, and we started looking at the machine learning aspect. So there's a group of plants which remain healthy. Parallelly, a group of plants get infected by some mechanism, and then we just monitor the growth of the plants. So this gives us, this takes us one level better in the sense, yes, we will detect, but the point at which we detect help us predict. So for example, in the first week of the crop, if we can say, oh, there is a possibility that this disease is going to infect just based on the image, that is what we call as prediction. Okay? So it's like, think of this as early disease prediction. Okay? And then, which means we can classify a given image as it's healthy, early stage infected or late stage infection. But everything else kind of more or less remains same because our inputs are only with things which are changing here. And the data set, of course, is a very different data set. So again, though it's a controlled experiment, I mean, 3 months or 4 months of work by a PhD student who's actually in that area of, let's say, plant growth and so on, she could actually gather this much of data. It's about 1,000 images, which were kind of curated data in some sense. I think it's like feeding the child and see how it goes. Something similar she did with plants. Of course, this is new for us probably, but they like doing this, and this is very important. Based on that experiment, so we had this breakup of healthy, early, and late. Again, here the early or late is some inferences which we made manually. I mean, the scientists looked at it and said, "Oh, this is probably infected," and that's how so we could probably do better. But here again, this is not like we didn't have the luxury of larger number of images. However, we wanted to go ahead and try this. So just note this, I'll come back to the one point later. So just see in this image in the early, there is a white tag. I mean, that just happened to be the group of plants which I had this white tag. So here again, in the onion, something I didn't talk about is the pre-processing. The way I showed the images, you saw there were different scales of images. So any background removal might have affected our result. So we didn't do any pre-processing in the onion. But in the tomato plant, like as you see the bottom one, we knew this is a control experiment where are things which we could easily remove. And so we applied this pre-processing so that we only have the foreground, which is the leaf and the plant related thing. So this helps the model also, like once we have a kind of cleaner background or no background in some sense, the model focuses on regions of interest. So this was one thing which we did with this tomato experiments. But other approach remains the same. So start with a plant village, fine tune it for the tomato, and then obtain results. So here, there it was a binary one. Here we had 3 classes, and we wanted to see how we do well, right? So just to kind of give a visual idea. So this is a image corresponding to a healthy tomato plant, and the model did predict reasonably well that it is healthy. Similarly, this is a early infected plant. Here again, you can see that it did predict that it's a early infected leaf. Finally, the disease one, which I mean, very clear even for humans. So the model also doesn't make much mistake. Okay? The mistakes are usually between this early and disease, which could be because of our labeling also. Finally, with this, so there are several columns here. This may not be that important. So when the images were captured, the whole plant was captured, and then we wanted to be closer to the plant village dataset. So these were cropped. So that's what this cropped here means. Image unbalance is always there, and one set we didn't do any correction for imbalance data, and the other set we did correction for imbalance, and that's this random sampling approach. And finally, if you use both pre-processing and the random sampling, and that's what is shown at the last column, and this is what is of interest to us. So for this tomato data set of about 1,000 images, so we have an F score of 0.871 and accuracy of 86.1. Again, certainly there is, again, it's like since it's work in progress, we expect these numbers to be improved and increased, but that improvement and increase depends maybe also on the labeling part of what we say is yearly and what we say as disease, right? So that's something which is very challenging. Of course, these are inputs from the scientists who work in this, so we hope we'll do better. There could be other machine learning approaches also, which we want to. So for example, all the few shot and other things which we didn't extend here, but that's possibly one of the things we could do. Just one point is what I wanted to say is this tag I mentioned here. I don't have the GradCam. Sorry. Yeah. This tag here, when we initially did our experiments, this tag was always saying that indicating to us that this is the early stage thing. So we got very good numbers. Like this 86 was like 95 or something. So then when we started applying our GradCam, then we realized that no, it's not actually the leaf which was saying this is early infected. It was something in the background which said all the early infections had this tag. So it was always saying early, which we were doing better. So that just to kind of say that, I mean, I think sanity checks on all these models is very important, and it's true for any ML model, but certainly here also. So these were, I mean, I think we're happy with what we have now, but we want to go further. So kind of that's my last slide. So it's like, so this to summarize, certainly ML and deep learning based models have been effective in detecting with very less effort. We only had to fine tune with the data set. But if we need better, let's say, for example, the kind of things which I was talking with, like tomato, like when is that's actually the challenging problem. When does the plant starts getting infected? That point of early detection is important. So that's why prediction certainly is something which we are looking forward. Other problem which we realized, so what I didn't talk about is, so yes, we fine-tuned on plant village, it worked on onion better. We fine-tuned on plant village, it worked on tomato better. We tried applying this to soybeans, which Professor Chris had looked at. Surprisingly, it didn't do that well, actually, the one without, if you just take an ImageNet-based ResNet models and just apply it on soybeans, that seemed to do better than the one which trained on plant life. So then we kind of course, independent of it also, I think Chris had this idea, but then we got interested in, okay, which data set to pre-train or fine-tune on. So then we are starting to look at data set similarities, metrics to look at it and see whether that is applicable to, of course, it may not be just for agriculture, but our focus right now is to just look at what happens in the context of agriculture, given the variety of plants, crops, regions, how well could we generalize it. So this could be something which we are hoping will be kind of interesting as we go forward. I have not talked about this, though I alluded to it in the beginning, that this time series correlating that with the image inferences is what is going to really help us. And the other part which we just started is also the images which I showed you were all kind of ground images taken in the ground. But now the work which Chris had done is on UAV images. So we are also looking at possibility of deploying drones to capture such images, and how well can we just apply these models, or there are things which we want to do to make them better. That's kind of one of the work which we just started. And the motivation here for us is we are actually going to do this so that it gets to the final user, which is the farmer, and say, oh, it really helped or not. So that's why we are kind of more, that's driving us in doing this, some of these things. And the bigger goal for us is to generalize. So once we do onion and tomato, can we just have a model which does for any crop? Of course, there are things which are different. So how does our model capture this? And we're hoping that this will come out of our collaborations with Chris and the team here in ICICLE, leading to other things in agriculture. So this is kind of what I had. If there are any questions, I'm glad to take these questions.
You have a few minutes for questions. Related work.
So you achieved very good results with your by using foundational models.
Yeah.
I was wondering, inside of the agricultural community, which is in rural areas, if there are any challenges deploying those foundational models, since connectivity might be an issue with the side, and running them on site would obviously be really expensive. So can you elaborate on the challenges and what you need to do about it?
Yeah, I think it's a good question. And the question was, when I talked about foundation model, I just sidestepped what these foundation models are. As was rightly pointed, foundation models are really huge models. I think you need large GPU machines to run them, even for the inference part. So our objective was to look at, so as I said, one of the challenges we have, even when we collect large amount of data, labeling this data is going to be a challenge. So one of the motivations for us first was to just try these foundation models on agriculture data. The second one was, so now these foundation models can help us kind of labeling unlabeled data. And once we have this labeled data, then any of these smaller models could help us do. So from a practical point of view, yes, I agree, this cannot be used in a farm and we can't kind of get data or do anything over the internet or the cloud. That wasn't our aim. Our aim is to mainly do this in wherever possible, but get labels out of this foundation model, because that's again not very new. I think people have started doing that labeling of unlabeled data using good models. So we'd probably use the same way. But as I said, even before that, is one challenge which we still need to address for the agriculture thing is how to come up with these good labels, which will help us make this model more effective.
So to clarify, that foundational models are only used at training time. They're not used when you need to inference.
No, so they could be used as inference. What we will do is we'll assume that this model is good. If we kind of have good confidence on the model, it's in the inference time, we give, let's say, for example, a leaf or with infection, it should say that this is infected. So that is happening in the, it's a testing for the model, but that's done offline, meaning we just infer, we get all our unlabeled data, we send this unlabeled data as test data to these foundation models, and they will give us labels. We will rely on that label. So we need a confidence measure on that label. So maybe this will give us 95% confidence on the label, which means that's a good enough label for us for a smaller model to work on. Then we will move away from the foundation model. We will go to, let's say, the DenseNet 51 or some very small model, which will now be fine-tuned using larger data, because that's a smaller model which can be fine-tuned faster and then deployed also. I understand there are 2-3 steps in between, but the hope is that we could do this.
We do have a hard stop at 11. Because this room is previously reserved. Is there anyone on Zoom that had a question? If so, we're not monitoring it, so can you unmute and ask? Oh, you are, okay. So then, the last one that I'll ask them, Rajbabu, is just wondering, thinking more generally about the strategy behind some of the works that you've taken, right? So there are a number of AI techniques to try. And, one of my takeaways is that as you try different AI techniques, you discover that digital agriculture looks very different than traditional image processing, right? And so you try these techniques and they work for traditional image, but they don't work for digital ag. Or maybe they do work, they work not as well, etc.
Chris, they can't hear you.
They can't.
Yeah.
Oh,
I don't think that mic is working. You probably need to be closer to this.
That's weird. I thought I had the mic set up. So I guess the question is, what does it look like in the future? Do you think it is better to do a deep dive into those AI techniques and keep trying to improve them? Or do you think it's better to keep trying new AI techniques as they're coming out to see what could be used off the shelf for digital agriculture?
Yeah, so I think based on whatever we have seen, I think it's better to just focus on existing models which are known well. The main reason being, so right now this kind of a one-sided view. So of course we started including agricultural scientists and scientists who are in the field and who know about this problem better. Even that I think it is not complete. So that's why I would rather just look at models which we know already do well. How effective will they be for this agriculture problem with the agricultural scientists in the loop? I think that's kind of a very important part, which if it is missed now, we will just be, I mean, the whole ML, the way the doubts we have about ML, whether it is ethical, all those things are beyond, I mean, they will become even more difficult. So I think it's better to focus on models which are already doing, approaches which are doing well, and then only then move on to, I mean, as a course project, yes, clip models can be tried, all that can be done. But as a solution that could be deployed, I think the confidence levels have to be higher, but more importantly, involve the real people who know about this problem more. Image processing people may not know more. Actually, it's agriculture scientists who knows more. So keep them in the loop, make these models stronger, and then go for machine learning techniques, which may help. I think that's
to be continued over lunch. I think we should thank our speaker.
yeah.